Hello, my name is Isaiah Jardulo. I'm a fourth year neuroscience and biology double major. I'm currently a member in the Bushbeck Lab, and today I'm going to be discussing my project involving jumping spider optics after viewing far and close objects. So first off, a little bit of background. The big question that I'm trying to answer here is how exactly do jumping spiders use their eyes to hunt their prey? Or how exactly do they use their large anterior median eyes to hunt their prey? Now, in the sensory biology community, there's really two big points of view at how spiders use their anterior median eyes. The first is what I like to call the classical view, and this is the idea that spiders are really unable to focus on images. So distance is really assessed by the amount of defocus in an image. So this kind of states that jumping spider vision is static, thus unable to focus. The second is what I like to call the alternative view. And this is really based on preliminary data from the Nelson Lab at University of Canterbury. So you have this really unique eye tracking hardware that allows them to track spider vision as they're hunting prey or looking at far or close crickets. What they noticed here, though, is that there is a slight change in photoreceptor size whenever spiders are looking at a far or a close object. Now, this could state that there is a focusing mechanism in their eyes, but sadly the data was unable to be analyzed because they couldn't get real clear images of photoreceptors, so it was hard to quantify differences in photoreceptor size. So this is really where my project comes into play here. The major goal of my project was to assess whether the classical or the alternative view is more explanatory in spider vision. Now, in my lab, the Bushbeck Lab, we have this unique tool called the micro-ophthalmoscope that allows us to get clear, high-resolution images of photoreceptors. So we can project close or far objects to spiders, and we can take images of their photoreceptors to tell if there is indeed a change in photoreceptor size. So the big thing here is how exactly are we going to use our ophthalmoscope to project images of spiders? And the answer really lies in figure A. So by putting a semi-permeable mirror on the objective lens seen in green, we could project far or close crickets to the spiders. Now, when the spider would respond to that cricket by either moving its legs or hunching its back like it was about to jump, we would shut the lights off and we would image their photoreceptors like we usually do in our lab. Now, the logic behind this is if the spiders can actually focus their eyes, then that would be visualized on the images we take on our ophthalmoscope as a change in photoreceptor size. Now that we've really gotten into our approach at how we're going to use our ophthalmoscope, let's get into some physics as to how this should work or why this will work and why we should see a change in photoreceptor size if the spiders can focus. So really this lies in some physics of optics. So as you can see in the figure provided, whenever a close cricket is projected to the spider, in order to accommodate that, if they can actually focus, then the spider will actually have to move its retina back slightly, as you can see in blue. Now, when the spider moves its retina back, the image that we're going to get on our ophthalmoscope will be slightly smaller. Now that we've gotten into the background physics and our approach, so how exactly did we quantify the raw images taken on our ophthalmoscope? So as you can see to the left, here's a raw image of a close and a far cricket. Now to the right, you can see we have how we used or how we quantified them. So basically what we did with the raw images is we took them and we used Adobe Photoshop to isolate the photoreceptors, and then we would crop and overlay the far and the close cricket to make sure we had a fair comparison or we had a fair overlay, and then we would isolate the close layer and we would isolate the far layer, and we would quantify them as pixel density. Now pixel density is just another way of saying photoreceptor area. So all in all, we had a total of 9 spiders that were analyzed, totaling out to being 15 anterior median eyes. Now we should have had 18 total eyes, but some of the spiders and data had to be thrown out because either A, it was too blurry, not quantifiable, or B, the spider just wasn't focusing on the cricket that particular day that we were imaging. So after various statistical analyses and t-tests, we found a p-value to be greater than 0.05. So what this means is there was actually no statistically significant difference between when a spider is viewing a far versus a close cricket. So really, in conclusion, what can we say about the p-value being greater than 0.05? So what this means for our project is there was really no difference when a spider was viewing a far versus a close cricket. Now this is more so in line with the classical view that spiders are unable to focus on images and their vision is static. There were a few limitations in our project though. The first being there could have been, when we turned the light off to image the spider could have lost its focus that it had when it was viewing the cricket. In addition, the time frame that it took for us to turn the light off and image their photoreceptors could have been outside of the window that the spider actually focused. So thus we could have missed the spider actually focusing. Overall, I would like to thank the Department of Biology and Department of Neuroscience for funding my research over the summers through STEM fellowships. I would like to thank Dr. Bushbeck's NSF grant, and I would also like to thank the Bushbeck Lab for helping me with data analysis and support.